everybody. Great pleasure to be here. Thank you for the invitation. I will assume that everything works technically, that you see me and my presentation. If not, please somebody jump in and yell. So I will start right now. So first, I would like to tell you a few words about me from the perspective of this talk, to explain you why am I talking about this stuff. So how are our brains different from our artificial intelligence? So I am an expert in both fields. I've been at the Max Planck Institute for Brain Research here in Frankfurt for many years, too many years. So I was running a neurophysiological laboratory. So I worked with real brains and studied real brains. So I know a lot about brains. But also, in the last 4 or 5 years, I've been professionally active as a data scientist, machine learning developer. So I know also lots about AI. So I see differences from one world and the other world. And I think some differences are stunning and some differences are really important to understand the future of AI. What are we missing? What we have achieved or what we still need to achieve? And that's what this talk is about, right? So to set the stage, let us look at this guy here, right? So that's a kind of our dream robot that we would all like to have at home, right? Somebody who can take care of our household. And although everyone has something like this in mind, we don't have one at home. We don't, still. All we got is something like this. That's the best we could do today. And it's not enough because there's lots of things that need to be done. In our households, there's lots of mess to be taken care of. There is a lot of, stuff to be ironed, dogs to be walked, and so on. So why are robot companies not selling such robots to us? I think everyone would like to have one. And so here's an example of a robot on the left side from the company Boston Dynamics. And they made a robot do backflips. And backflips are impressive, especially when humans do them, because it's a hard thing to do. Doing dishes by humans is not impressive. And yet, Boston Dynamics does not sell robots that do dishes. Now, the question is, did they mix up maybe the market? How much need for robots that do backflips is there on the market? What do you think? And how much need on the market is there for robots that can do dishes, right? So I think everybody would agree that, dishes selling robot would sell better, and yet we don't have ones. So why don't we have? Why do they don't give us some? And what is behind that problem is something that's called Moravec's paradox. And basically, this paradox is telling us that things that are easy for machines, easy for robots, easy for AI are hard for humans, and things that are easy for humans are hard for the machines. So backflips are hard for humans, easier for machines. Doing dishes is easy for humans and hard for machines, right? And the reason behind all that is that biological brains and machines work differently. And that's what this talk is about. What are the key differences, right? So let's go through them one by one. Difference number one is the type of errors we make. Like we humans make different types of errors than machines do. And to illustrate that, please watch this clock here and watch at the second hand and detect where the second hand skips 1 second. So the point of my demo is that it's easy to distract us, right? If something happened on the right side of the screen, you have to move your eyes on the right side, check what happened over there, and then you may have missed the skip of a second, right? And that's what we humans are really bad at. That's the kind of mistake we do all the time, right? And machines don't. Machines can be focused and keep their focus, attention, what they're doing, and they don't miss it every single time. Machines make a different type of errors, which maybe we could call stupidity errors, like dumbness errors. So here's an example, illustration of how machines can do things wrong in a very old movie by Charlie Chaplin called Modern Times, where at the beginning of this scene, they created a machine that can feed workers in a factory, and at the beginning everything works fine, and then the machine even can help clean the mouth of the people having lunch. But then something goes wrong with the machine, and this doesn't work anymore really well. And the point is that machine cannot do anything about it. When something goes wrong, the machine just keeps doing the wrong things, cannot correct. We humans can correct quite easily, or much more easy than a machine. Right? So that's the first difference. The second difference is about concepts. We humans have concepts, and let us consider a concept of a chair, and how do we recognize a chair? How do machines recognize a chair? How do humans recognize a chair? So if you want to create a deep learning network, for example, that will detect a chair as opposed to a flower or a car or a face or something like that. What you will need is to give it a lot of examples of chairs, like these examples here. And you may need, 100,000 or something to have a relatively fairly good detection of chairs. And then you would say, okay, my AI can do chairs, and we humans can do chairs, but there's still a difference, right? So I'm going to give you examples now of chairs that this AI will have really hard time with, like this chair here, or that chair, or this chair. And here's another chair. I have even more weird chairs that AI would fail to detect, and we humans have no problem seeing the chairs. This one, and that one, and this one, and that one, right? So for example, this last one, any deep learning solution that was trained on recognizing different objects and was trained with prototypical chairs would never recognize a chair here, but would recognize a suitcase, right? And why is the difference? Where is the difference? That's because the concept that we humans have about a chair doesn't have to do much with what a chair looks like, but it has to do with the function. And the function of the chair is for us to sit. The chair is something where we can sit and relax, and if we are tired, right? So basically our concept of a chair looks like this. It's something that brings our body in a certain position. It's not the elements, the legs of a chair, the colors, the components. It doesn't matter. What matters if this thing can bring our body in this position, right? And then we can also have different types of chairs for different types of comfort, for different types of body position. All of them without any features, classical features that we put in the machine learning of AI, right? But that's a very big, important difference. So here's some more weird chairs, just to make the point a little more better, right? Okay, all of these chairs are difficult or literally impossible to be recognized by AI. Now, how do we use our concepts? So I mentioned that we need thousands, maybe hundreds of thousands of examples of chairs to be pretty good in chairs for AI, and still AI will fail with lots of these weird chairs. Now, how about the concept of car? Same thing. To recognize a car, an AI would need thousands, 100,000, million examples of cars to recognize a car. And we humans, well, this kid here could play with the car for an hour, for example, with one single car. And after that, be able to recognize cars, perhaps as good as it is being done by an AI, or better. But it's even more what a kid can do. If you go and draw something like this for a kid, and you say it's a car, the kid will accept it as a car. And the deep learning network that was trained on photographs of cars will never recognize this as a car. And kid would immediately understand this. This is a car, okay, fine. One example. But it goes even better than that. After we have drawn this, we could draw something like this and ask a kid, what is that? And if the kid has ever played with a single train, it would generalize from this single train and infer that this should be a train. If this was the car before, now this is a train. But it gets even better with our human concepts. We could go back to this drawing and say, look, this is not a car anymore. Now this thing is a table with 2 chairs. No problem for a human and for a kid. They will just recognize, they will just reorganize their head, reorganize their mind, and now see a table with 2 chairs. And then we go back to this one, and then it's no problem to see here a classroom, for example, or a scene from a restaurant. Right? So this is the power of our human concepts that machines still don't have. And it is these concepts that makes us so smart and so much more intelligent and so much more capable than machines are. Right? So here's a little bit of an overview of the most important concepts we have. One of the most important concepts that we have is a concept of self, of ourselves, right? So this would have a component like name and what we look like, how old we are, skills that we have, what we like, dislike, which friends we have, and all kinds of stuff about ourselves. Then another important concept that we have, like critical, very, very important one, is time. Because everything we know, everything that happens to us, we organize in time, somehow in a timeline, right? So within that concept, we have a sub-concept of yesterday, of future, or tomorrow, last vacation, my birthday party, history. Everything's organized in a time, right? Yet another very important complex concept that we have is our profession, where we learn lots of skills in lots of things relevant to our profession, right? So that which makes us who we are. And of course, we have many other concepts, right? Even self-awareness is basically based on a concept of self, right? And which makes it possible that we reflect and do something like this guy did here. Sometime in a history, it happened for the first time ever that some human or some creature on the way to become human for the first time self-reflected and thought something like this: holy smoke, I am standing here, I am me, right? Machines don't do that yet because they don't have all these concepts, right? So concepts are great, and that's our second difference between us humans and the machines. Now, let's talk about context. Context is very important, right? We humans work in context, which means basically that we humans are not independent of context. What we do in every second and how we will respond in every second depends on what happens just a second before, or 5 seconds before, or a minute before. It's all interdependent. For machines, they're contextless, more or less, right? It's very hard to machines to give them context. So to illustrate that, for the purpose of this talk, I have asked Cortana a context question. First, I asked Cortana, what is the capital of Germany? And it correctly answered Berlin. And then I said the following: and of France? And the reply I got was, I pulled some images of France for you. So Cortana did not understand a very basic, simple context, right? Because it's not a part of AI. Yes, sure, the engineers at Microsoft could implement certain context for this particular situation, but the context is not natural to the AI solutions, to our technology. So every single case would have to be implemented separately, which doesn't really work generally, right? For us, for our brains, it's just natural. That's how our brains work. Okay. Now, when doing this, I noticed one interesting thing about our assistant software, right? So I looked at the logo. Look at the logo of Siri. It's a circuit. Look at the logo of Alexa. It's a circuit. Look at the logo of Cortana. It's a circuit. What do you think is the logo for Google Assistant? It's a lot of circuits. It's actually 5 circuits. Everywhere circuit, 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 circuit. Why circuits? Why all the assistants have circuit? And it's a valid question to answer that. And I try to answer it. And then I remember the original assistant from science fiction. Before assistants really existed, there was one assistant in science fiction that is quite famous, and it's this one. It's called HAL 5000 from Odyssey. Space Odyssey. So maybe HAL is the originator of all these circuits. And then remember this guy here, right? Which is a moving circuit and an assistant at home. So there's something going on with circuits here, right? Okay. Now, context. For machines, they like random stuff. They prefer random stuff. Actually, deep learning requires random stuff to be randomized even to be able to learn properly. And this brings us to our fourth difference. And this is about learning, how differently machines learn from humans. Right? Now, to do that, to illustrate that, I have created a video that I will show you in a moment. And this video illustrates what is it like to be a deep learning network. I created a video that kind of simulates the sequence of materials that deep learning network receives in order to learn 2 categories. In this case, this will be categories living or not living, right? And I use some random images. So I literally Googled random images. I collected them, separated them into living and non-living part, and then look at the video, please. What it looks like to learn if you are a deep learning network. Okay, so how was the experience for you personally? Probably not very good. How much did you learn? Probably not a lot, because it's not suitable for human way of learning. It's suitable only for deep learning, and deep learning actually requires randomized. If the examples are not randomized, then deep learning will not learn properly, it will produce biases and so on, right? But how do we humans learn better? And I have an example. Now, to do this example, I have exactly the same images, exactly the same order, but I add one thing that deep learning doesn't care about, but we humans care about. I make story out of it. Story means context. Right? Story is a context. One event happens after another event, and they make sense to us. So they follow one from the other. So let's see the same sequence of images with a story. Right? Once upon a time lived a dwarf named Pepito. Pepito had a dog, Barfi. One day they hit the road and tossed a coin to decide where to go. And decided to reach Antarctica. They didn't trust airplanes, so they traveled through Africa by train. When they reached South Africa, they waited for a boat. While waiting, they went for a dive. And they met Horatius, who took them to Antarctica on his back. And success, finally. And the same sequence of images that you have seen, but making story. Now you remember it. Now you can probably remember all the or majority of the images that have been presented. Probably you will remember them in a week from now as well. When somebody asks you what was the presentation about, what was the story about, you will remember most of it because it makes story that makes sense to it. It's context, and we do not only look understand context and stories in a time frame, but also in a space. So if there is a static image, like this one that you see in front of you, the way humans understand this image is not just a snapshot. So what the deep learning network would do is just snapshot and parallel processing, stage, boom, and at the end it would identify some objects. What we do, we see one thing on the image, we detect something, one part of the image, then this, whatever we recognize, becomes a context for detecting something else in the image, which becomes a context for detecting something else in the image. So again, we build a story even though this image is static, right? So that's a famous painting from a Russian painter called Ilya Repin. And the name of the painting is "They Did Not They Did Not Expect Him." Right, so you can see here how you could build an interesting story. This male person walking in, everybody watching at him, being surprised, and so on. But it takes time to build a story and build this understanding. And neuroscientists did some research on paintings like that, and what you can see here is our eye movements, where people look at which places in the image people look over time. And as you can see, first it takes time. You have to explore the scene for a while, and then people look mostly in the faces, because in this particular image, especially the faces tell a lot about the story. Where is who looking and what kind of expression and motion they have. So, right? Okay. All right. The next difference is that we don't only have concepts, we can create new concepts on the fly. Right? We don't need 6 million examples of something to create a concept. We just create a new one, bam. So I will create a new concept for you right now, just to illustrate that. And this is a concept of banana riding a bicycle. Right? Just saying this sentence could be enough, but I can reinforce this concept with a picture, banana riding on a bicycle. Actually, I can reinforce even more this to make a story. I'll again make a very short story, and also some emotional story, right? Emotions help as well. So here we go. You have a poor village somewhere far away in Africa, probably, and people over there walk long distances and work hard for living. It's a hard life, and one of the activities is collecting and selling bananas. And the transportation for these bananas is bicycle. People don't ride bicycle; it's bananas who ride the bicycle, and people push them. That's how they sell them. Right? So I just created a new concept for you: banana riding on bicycle. Probably useless concept. But also something I made up just randomly, Googled images, made it for you, right? Works for us. You will remember banana riding bicycle also. If somebody asks you 6 months from now, you will remember it, right? Good. So difference number 6, working memory. We humans have working memory, and machines don't. So let's see what working memory is. Let me illustrate that. And to illustrate it, I will just give you a task. So your task is to first to watch something. It will appear for a short period of time. Then there will be a break. Then there will be a test. Okay. So ready? What changed? The question is what changed? And most of you will probably be able to tell that actually 2 of the squares replaced positions, or 2 colors replaced the positions, right? Okay, but that's the limit of our working memory. Our working memory is limited to about 4 things. Now, to illustrate that, let me show you another version of this task, a very similar one. Okay, ready? So was this one presented or not in the original sequence? Now, you can answer this with confidence only if you're Chinese or you are expert or skilled in using Chinese characters. If you are not skilled in using Chinese character, you have no chances. That means that, what that means? This means that Working memory relies on the concepts. And if you have a concept, like you have a concept for red color, green color, yellow color, you can do up to 4 things. If you don't have a concept for symbols like this symbol here, then you have no idea whether this was presented or not in the previous group of 4. And the correct answer is, just if you're curious, yes, it was presented, but I turned it around 180 degrees, or I turned it upside down. So the one on the right. Yeah. Okay. So we have also working memory, this weird thing of very limited capacity, and that machines don't have. What is working memory? Why do we have it? It looks kind of ridiculous. A machine can memorize millions of things instantaneously, and we can memorize 4. That doesn't seem first fair, and it seems kind of crazy and ridiculous. But the point behind that is that our working memory is actually a place where we think, where we do work intelligently. That's the place where we do everything else that I mentioned before, where we learn, where we make inferences, where we pay attention, where we lose attention, where we activate concepts, where we come up with new concepts. This is what our working memory is doing. It's not just a memory, it's working. It's being intelligent, right? And that's why it's only 4, but it's 4 of maximum power of our mind, which machines are really far away of reaching. And the last difference is difference number 7, which is number of things we can deal with rapidly. So to see that, now we are going back to the point where machines are better than us. Now, first take a look here and decide which of these 2 characters is actually number 5 laying down and which one is number 2 laying down. Okay, and that's pretty easy. But now find number 2 laying down. Right? Now this is really, really hard. And you have to do it very slowly, and this thing is here. So in the middle right side, a little more on the right side. Machines, of course, can very quickly find it, and for us it's difficult. Why? Again, the same reason. We are using our full intelligent conceptual power for doing such simple and dumb tasks, or at least it's simple and dumb for machines. It's hard for us. The same thing as the first problem we had, like where we had this vigilance problem. We couldn't monitor forever easily accurately the second hand of a clock. Again, because our concepts were working out, understanding what was going on in the world, and when the destructor came, we had to process it and apply our conceptual intelligence on it. And machines don't have conceptual intelligence; they have nothing to apply, and therefore they're able to monitor things accurately. So let's get to the conclusions. The brain and machines work in fundamentally different ways. I think we have established that. Only we use concepts properly, and context, and stories, and machines have none of it. Machines are not anywhere close to reaching human intelligence, no matter what popular science tells you. But probably you guys are all in AI, actively working, and you know that anyway. And for the foreseeable future, humans will have jobs. Machines will not take over because, again, we have concepts and we work with context and we understand and deal with stories. Now, let me get back to the initial problem of doing dishes. Right? So there's a fundamental difference between human intelligence, but not only human, biological intelligence in general, and machine intelligence. And to do dishes, you don't need human intelligence, you need biological intelligence, biological principles. So animals can do dishes. That's my point here. And to prove that point, I would like to show you this video.
Oeh, is dat veel, papa. Was zo, zei. Was zo veel, papa. Dit is zo lekker, papa. Terug op af, gaat naar joh. Zei.
All right, good. I think that's enough. So thank you very much, everybody. That is the end of my presentation.